All right. Well, welcome everybody to week 2 of our R statistics workshop. We're going to be kind of building upon last week where we went over a lot of more descriptive data analysis, more exploratory data analysis, introduced some basic concepts. Today we're going to be going through a very practical lesson, something you will use all the time, which is hypothesis testing, more importantly, the t-test, non-parametric alternatives. And then we'll look into a little just at the end on power analysis and sample size and multiple p-value testing correction. So today we're really going to be looking at our learning objectives are to understand hypothesis testing framework, how to perform and interpret various t-tests, how do you make assumptions for these parametric tests, what are some non-parametric alternatives when these assumptions don't play out, and then kind of how to basically calculate and interpret some effect sizes, and also looking at some multiple testing corrections when you're looking at a lot of samples, comparing a lot of samples in your p-values. First, we're just loading all the required libraries. I think the things we're doing, the new things for today are this R statics package, which just allows for a lot of very tidyverse friendly statistics, a CAR package for Levene's test, which is the equal variance test we'll see, EFF size for effect size calculations, PYR for power analysis, and then here we go, this ggpubr is really good for publication quality effects. These are all kind of our new packages. You may need to install them before you get going. So first, just I'm going to get on my stump and like an old man and complain. Let's talk about hypothesis testing first, right? So you guys all know about hypothesis testing. A lot of this today is going to be a lot of review, simple things you already know, but slanted toward the ability to use R for statistics here. Remember, R was basically completely made for statistics to be able to replace Microsoft Excel and other corporate, SPSS or whatever, the IBM version. R was made and its vectorized ability to be powerful in the statistics world here. So that's why we're really learning how to apply it. So some of these concepts are really obvious, but we're going to be applying them in the R array, right? So your null hypothesis, you guys know, you're basically testing this null hypothesis, and we need strong evidence, so it's basically a low p-value to be able to reject this null hypothesis and have a significant result, right? So one thing to talk about I think is interesting is how things have changed. When I grew up, we always learned the standard hypothesis-driven way of scientific research, right? Where you would state the hypothesis, start off, have a great idea, set your significance level, collect data, you do your t-tests, and make a decision based on the p-value. But really, things have changed, and I know this is pretty obvious, but putting it in the larger, looking from a higher view, I think it's important to think about this. So now we basically set our significance value first. We collect all our data, like let's say a bunch of expression data. Then we calculate our p-values, and we're like, hey, these genes are different, and they must have to do with this drug. And then we make a hypothesis, and then we show that the data fits, and we're like, now our drug works, or it might work, right? And this is kind of the way we do things now, and I don't know, it's a little bit shady to do it this way, but I think going forward, I want you to really make sure you put these in context to try to have a hypothesis early on, even before you start your data. So just food for thought there. It's kind of interesting the way things have changed. Because, one thing we look at in p-values, we're looking at this distribution and when we calculate our p-value where only, 5% could actually be wrong, right? But I don't think that's really that extreme. 5% wrong is a lot, actually, in real life, if you think about it. So really think about that when in the context of your experiments, and realize you probably need a p-value way lower than 0.05 to really be significance, right? And realize that p-value is not everything. Sample size is important too. You could have a drug that reduces the tumor by 1% and it's significant, but who cares? The sample size is just so big it doesn't matter. Or you could have a drug that it only extends, only has a p-value of 0.06, which is not significant necessarily, but it extends life by 2 years in a small sample size. Well, this is such a huge difference. It's an important effect. We probably need to look farther on that. So just p-values aren't everything, and you need to look at things in the greater context. That's all basically what I'm saying here. So for today, we're going to be creating some just our own cancer research data sets. And first, I won't go too much how I created them, but you guys can kind of look through this and see, the same thing we've been doing in the past. I'm trying to I want a sample, I want a gene expression table based on, sample of patient IDs, and I'm just write my tibble first. I could write an as.data frame there. I'm just creating all my columns, right? My tissue type, are we normal or tumor, and an expression in 3 different genes here, BRCA1, TP53, and MYC. So that gives us kind of our patients, and this is just our first 6 rows of expression data. We have all our patients here. We'll have our tumor and normal below, and our expression of our 3 genes. So we can be able to have that ready for later on. And second, we want a paired data set. We want to do pair t-tests. So we want paired biomarker data here. And we're basically making a data frame where we have a range of patients and they have prostate cancer. And so we are going to look at their PSA value before and after, where we're expecting a treatment to lower our PSA probably, right? So we have a column of, if you see here, we have a column of before and after for our PSA, and we also have a PSA change and percent change as well. And for our third data set, we're making a drug efficacy study, kind of to mimic clinical trial data here. And here we'll have basically a treatment. I'm making here I factor out placebo A, drug A and B, and then we have like a baseline tumor size, let's just say in centimeters or so, and a final tumor size, right? And we basically throw this together into a nice table here, and basically see we have 3 populations, 40 in each for our drug A and B versus our placebo, and we see our kind of reduction in our tumor size based on that. So these are the kind of data sets we can use going forward in this lesson. So just to start off, the easiest thing possible, a 1 sample t-test. We're just comparing one single group's mean against a normal reference value to see if we see a change. So for example, we can look at our PSA data set, right, our prostate cancer data set, and say, for example, is the average PSA level seen in all our patients, before treatment, different than the healthy population? So we're going to basically look at all our PSAs, see if they're different than normal. And we probably expect it to be higher, right, since they're cancer patients. So first, we're just going to look at organize our data set a little bit. We're going to grab out just our patient ID and our PSA before and call that our PSA data. And then, so here we have just our patient ID and our PSA value before. Then we're kind of just going to look at the summary of all of that. So if you look at that way, we have 25 patients, and really just a summary of our patients here. We have our mean and our median and our standard deviation, everything of our difference and our change, and we're just basically looking at our PSA value levels in our patient, and we want to basically compare these in a histogram. And first, we are going to make so we basically make that backdrop on the background, right, for our GG plot, or just our PSA data, where we have X equals just PSA before. We're only looking at the PSA before here, right? And we're going to make a GM histogram, and we want the Y axis to be density. That's because we're adding in GM density. Remember our last lesson, if we want to leave that blank here, we would have frequency for our Y values. But in this instance, we want the density to be our Y-axis. So we'll have our double plot here. So then we add on our GM density like before, and we're adding 2 vertical lines, GM by GMV line, to basically show our healthy reference and our, which is 4, right? And our mean sample, which is going to be 42 there. What else we're doing here? And then we're just kind of labeling everything. And then we see our histogram here. We kind of have 2 populations. One that's probably the cancer is really low, and our normal population in our histogram, and where we can compare against the healthy reference with our histogram and our density plot to show that it is much higher. But is it significantly higher? So to do this, we want to check our t-test. And to do this, we use our t.test. It couldn't be simpler, right? So I'm going to show you two things along the way as we go, where we will do it the base R way and the tidyverse way. And I won't go really into the tidyverse way because I believe the R base way is the best and simplest way to do it. Normally I prefer tidyverse, but in this instance, some of the basic base R functions I think are just simpler for us. So what I'll have here is each time I do a sample calculation with base R, below it I will put the tidy version, which will give us the exact same result, just in a different way, maybe a little cleaner way. So let's start off with just the one sample t-test. We do t.test, and we're only looking at the population before, right? So we choose PSA data, $, PSA before. We're just grabbing a vector of that column of the PSA data that refers to the PSA before, and we're comparing it to the average being 4.0 in the healthy population. And if we just print the result for this t-test, you'll see here the p-value is 1.83 times 10 to the negative 10. So we're looking really good. It looks very significant here. And we will move on to just kind of tidying up that data. So I'm basically just taking the one sample t-test and I'm adding in a little bit of interpretation here. So we have a low p-value, a high t-statistic. Our mean is 41.93, our median actually, and which is our one sample t-test. We did it two-sided, and it is significant. So PSA levels are significantly different from our healthy reference in our data set. Today we'll mostly be doing two-sided for alternative, just so you know what two-sided means if you forgot. It's basically just saying that the value can be greater or less than the mean value. If it'd only be one or the other, we could pair it off to one-sided, greater or less, or things like that. But today really everything can be two-sided, so that's the fair way to do it. And now we look at the Cohen size, the effect size. So it's basically saying that we know how significant it is, but how different is it, right? And this is really, you can see more of the calculation here. It's the mean of the change minus the average divided by the standard deviation. And going forward, really, we'll have, you could do a Cohen dot d test, and we'll see that going forward. I just wanted to show you a very simple example of how you can actually calculate it without the package itself. You see the tidy version below, Cohen's _d, to get the same result there. And look at the effect size as 2.1, which we see in our interpretation. Anything over 0.08 is a large effect, where anything under 0.2 is a negligible effect. So this gives you an idea of how large the effect is, even though its significance. And we just kind of made a little bit of interpretation where we showed the difference is 37.99, strong low p-value, and where our conclusion that they are elevated in this instance. So now let's move to the two sample t-test. This is really comparing the means between two independent groups, right? This is something you use more and more. It's the most common one, right? You practically use this every day in biology research, right? It's just to get a quick view of two different data sets, right? So let's go ahead and make that, and let's go look at this. So first I'm just going to basically grab the data set, our gene expression data set, and look at simply the sample ID, the tissue type, and the BRCA1. Because we're going to be looking at, is BRCA1 gene expression different between tumor and normal? This is a very, very simple practical comparison. Normal tumor, is gene expression going to be different? So I'm basically just, like I said, I'm taking the sample ID, tissue type, and BRCA1. Based on that data, I'm going to group by tissue type, which stratifies into our two different things in our tissue type column, which is normal and tumor, and then just do some summary statistics to get an idea of what's going on, where we see the mean is much higher in the normal. So I would expect maybe BRCA1 to go down, which kind of makes sense because it's a tumor suppressor, right? So we see lower of that in the tumor. So let's just see if that is the case. So first we're going to once again visualize everything, and we're basically going to be visualizing using our box plot and our density plot. So for our box plot alone, we're just setting up the background, remember, use our BRCA1 data, set up our AES, X equals tissue type, right? And BRCA1 equals Y, and then we'll fill by the tissue type. at the X value, right? Then we'll add our GM box plot for our GM box plot, taking out our outliers by outlier shape equals an A, just like we did last time, We're adding our GM jitter so we can actually see our dots, and then we added that kind of cool stat summary median function where you add the diamond in the middle there so you can tell the mean versus the median, and then, added all our labels. And for our distribution plot, it's just a simple density plot here. So we're just do a ggplot BRCA data, x equals BRCA1, and because we're just one value, right? And then we just fill by tissue type to get the different answers. And we do just GM density, and we're able to get our plot here. So now we see our different distributions based on our tumor and normal, and see how kind of different they are. Where it looks like they're going to be lower in the tumor in general, and the normal distribution is much tighter if you look at that. So one thing we want to talk about today is you can't just run a t-test out of nowhere. You need to look at the data and look at some assumptions. Is this data normal? Does it have equal variance? These are two of the bigger ways to look at this. There's more in-depth ways. And this is really important because it will shape and change the way you adjust your functions and your parameters down the line based on these results. So the first thing we want to look at is the t-test assumptions here, right? Simply the normality. Is the data normally distributed? How distributed, how symmetrical is a distribution? How close is it to a normal distribution? And then two, are equal variance. Like how much do the variance spread out in each of these? What is the similar spread of values, right? Because we want those to be relatively equal, or they're really hard to look at, right? So like we did last week, we'll use the Shapiro-Wilk test to look at normality, and we're basically going to group by tissue type, already the way we had it, the BRCA1, and then just summarize. And by summarize, we'll add in our Shapiro statistics, just like last week, to get our values there. And then we'll see if Shapiro p-value is greater than 0.05, then that means it is normal. So that's what we want here. We want a greater than 0.05. And for Shapiro statistic, we're just using Shapiro.test, basically on our expression level, right? Because we have our matrix, and we're just wanting to look at the BRCA1 basic expression, and it kind of just grabs that column, right? And then we just want the statistic here. So we put, we call that column, we call it just the stat here. Where here we just want the p-value, we call just that value. Because basically what you're going to get here is you're going to get a statistic that's going to have a column for each of these things. So we just want to call these differently so we can put them in our table here. And that's all we're doing here. We're creating these two columns here, and our third column is at normal. So lo and behold, we have a pretty high statistics here, and our p-value is high as well, so this is normal. This data is normal, so that's good to know. And we move to the next step. We're just going to look at our QQ values as we did last week. Same exact thing as here. Here we just filtered out the rows. We grabbed our filter here is filtered rows, right? So in the data, we just chose all rows where BRCA is normal and all rows where BRCA is tumor. We just kind of did it a different way here. Depends on how the data was shaped, because we didn't do that group by first, right? So we needed to grab by rows, and then we just did a simple QQ norm and a simple QQ line. And that gives you the data here below. And you can see it falls pretty well along that line. It trails off a little bit on the edges, but for the most part, it looks pretty good there. So both our normals are value. We can see here that we're using the QQ plot. It's the same. So I'm going to show you another way to do the QQ plot using tidyverse. Or you can use QQ, GMQQ, and GMQQ line instead. And here, I just kind of did the same thing. I'm grabbing the BRCA, right? We can look at the BRCA1 data, and we can just sample by BRCA1 only using the tidyverse, kind of similar to how we did our actual t-test. And then we just add our QQ GM, QQ line GM. That just recapitulates the plots as above. And I just did a facet wrap by tissue type to split out our normal and tumor across the instead it won't be a stacked on top of each other, and they'll be better presentation. Sorry, I can't talk, right? So next, let's check for equal variance. So there's two ways to check for equal variance, right? The var.test, which is kind of the base R way of doing it, and just a common F-test, basically it's called. And then we'll use the Levine test, which can also be done by tidyverse down here, using the statics package, or remember the tidyverse always has that underscore here, and we'll get the same result as the Levine test up here. And we're basically just taking our normal and tumor values, which we already kind of defined right here, our normal tumors, we're making our QQ plots, so we can just take advantage of that. So we can, because it's just a vector, basically, it's just a vector of the values. It's just a vector of the values that are all normal, a vector in values that are all tumor, right? So that's how you call those two things for the VAR test. And Levine's just a little bit fancier. Instead of calling the two different, instead of splitting the two different columns, we're just doing BRCA1 by tissue type. So you can imagine like there's just columns, right? Where they're all BRCA1, right? There's a BRCA1 column and it's a tissue type column. Tissue type has both. So you can either select them out, filter them out, and separate them out into those two there, or you can just call, as a function of that. Same exact thing, right? Same exact thing. It just matters how the test you're doing wants the data oriented. So both these are exactly the same. Values are being called upon, and we have two different values. The Levine test, because it's a different value, right? And basically what we want is if the p-value is greater than 0.05, you're getting it has equal variance, right? So we don't want it to be 0.0. We want it to be greater than in each instance. And I just kind of made a data frame to put out our results of our our statistics for each one of them, and our p-values and answers. And we get an interesting result. We get opposite results, right? For our F tests, our p-value is significant, so therefore our variance is equal false. There's not equal variance. Our Levine test says the opposite. It's saying it is true. So what do we believe here? We got opposite answers, which happens all the time in bioinformatics, actually. So what do we do here? Well, looking into the literature a little closer, if you have both of them right, you feel the best about it. But if they're contrasting, the literature says to go to Levine's test. It's much more robust. So here we can just say we have a strong value of rejection in Levine's test. We can go with that based on that, and we can say there's equal variance. So this gives you a solution if there is a little bit of a contradiction there. And if you want to take it one step further, you can do here, you see this line here, you can do the Levine test and add in center equals median at the end. And basically, instead of looking at the mean differences, looking at the median differences, which are a little bit more robust. And if that comes through, then that's a kind of a sanity check. And then if you get a non-significant value, equal variance for that, you can feel even better about that, right? And in our instance, if we did that, I don't have the answer here. We did get it to be equal variance too, so we can have a little bit more belief in that value there, right? So there is equal variance. So we have normality and equal variance here. So that's really good. That's our best scenario. So here, now that we're doing a 2-sample t-test, here's the new way of doing this. T.test, right? And then I have two different things. Now I'm going to do BRCA1 as a function of a tissue type, right? And then I'm just going to put it what the data is. So it's looking at the data, and it's just looking at the BRCA1 column, and it's comparing the different tissue types, normal versus tumor, right? And we will put variance equals equal equals true, because that's what the Levine's test told us, right? Now, if Levine's test was false, or it didn't give us equal variance was false, and there wasn't equal variance here, instead of saying true, we would add false. And this would basically be the Welch's t-test. So this is a very well-known t-test, and it's used for a 2-sample t-test when the equal variance is equal to is not equal, or variance is not equal, right? So you put a false in there if you need to, and we put true in here for our case because that's our data, right? And then once again, here's the tidy way of doing it. It's basically very similar. It's exactly the same. It uses the backend R anyway, so it's the same thing. And here you would call the data. You would do your T with underscore t-test. Var equals true. Looks exactly the same, right? And that will give you your answer. Now, what I find is the tidy ones, just to kind of give you a heads up, they're very bare bone. They don't give you a lot of answers. The top ones give you a lot of data, the percent intervals, all that. there's a less data given them, but you can get it, but you got to keep adding on more pipes to get more information. If you want, and you can also do cool things by adding things on that you couldn't do with a normal R, base t-test. For instance, you can do what we're not doing here, but the t's you can do multiple testing. So you could adjust the p-value based on the Bonaferi method here. You could add significance. You could add the position you want on the graph. So you can keep adding a lot of different things on the tidy way. So that's something to think about. Because if you want to, especially once you have everything figured out and you want to redo your data, redo your code for the publication, it might be better to use tidy in that instance once you know what you're going to do, right? But I still think it's just simpler to do this. And we can do our multiple testing significance later. It's not hard to do outside of it. I mean, we already have our significance here, right? We know. So our value, is way below 0.05. We feel like those are significantly different, and we'll just kind of tidy it up here. We have a super low p-value, and your estimates are pretty different. And we can say that it is higher in our direction significant, and it is higher in the tumor data, right? I'm sorry, is lower in the tumor data. Let's see here. So now we want to do our effect size, basically. So we're just saying these two ones are different. And I was confusing myself here. Lower in the tumor data. So we use BRCA1 here for for the Cohen's test. And here, like I said before, you can actually do Cohen.d. There is a function. So we have our BRCA data, and we just set it. Remember how we split out our tissue types before? We could do the BRCA data by tissue type, but like we did below. But it likes it separated out. So the R1 likes it separated out. That's why we filtered out the column. So we could have used our normal values, our tumor values, but we're just kind of filtering again. So once again, we're just grabbing all the rows in the BRCA1 column that have normal versus tumor, right? So we're looking at our effect size, and we see effect size is 2/2, so that means it's a pretty strong effect size there. And so now we know there is a significance, and the tumor is lower, kind of what we expected. And so now let's plot it out and add our p-values on there, right? So we haven't talked about this. How do we add our p-values onto our plots? So there's several ways to do this. Several manual ways to do this, where we can just be able to direct the actual numbers on the plots themselves. But I think just a good way to do this is to use the ggpub-r and kind of get around it and add it into the ggplot at the end. So P1 just refers to the plot earlier I made. I just defined it here. It's exactly the same plot. It just doesn't have the actual p-value on it. And I'm using a function called stat compare means here. And basically, it kind of just redoes the t-test in base R exactly like you did it, and then just adds on the p-value there and the different comparisons you want them to be added. So it's really simple. You basically have already done the test, so you know what it is already, right? So we know t.test is our test. We know var.equals true, so that's good. Equal variance, don't have to worry about that, so it's because it's equal. And in our normality, we could have put, or basically just, we know it's a parametric test, so we know it's normal, so we control for our normal variance, and we added p.format to get our p-value. We could also add p.signif to get just stars instead. And when we put our comparisons, that lays out how we want these plots to look. And this matters more if you have multiple samples, but for one sample, it's really easy. You just make a list, and you put an order of the way you want the actual line to go, showing the p-value comparison. So we say normal to tumor, that gives us the line from normal to tumor. Our p.format gives us our 1.1 times 10 to the negative 10 on top, and that gives us our complete graph here. This is really the best way, I think the easiest way to add those on to the end. And you could also easily change these on and add them later, and mess with them too in Adobe too. it's not that hard to really build these, especially if you have one, you can just cut and paste it, things like that. Because things don't always come out perfect, right, for your Illustrator, right? So now that we've done kind of two sample t-tests, we compared two populations, right? So a bit of tease for next week. What if I wanted to compare all the populations? Well, there's a couple ways you could do this. Next week we'll talk about things like ANOVA and other ways of doing things. But you can also just do a multiple t-test. I mean, that's what SURAT does. If you're doing general RNA expression, and you're looking at the expression in between genes, it just does t-tests for every single possible calculation and then normalizes that and transforms the data. That's how you get your actual result. So doing multiple t-tests is still a powerful way of doing this that's used in the literature. So let's see how we would do this where we can compare all the genes at once. So basically the first thing we need to do is just kind of change up the actual expression data to be in a formulation that can be used by a ggplot. And I kind of wanted just to show you this, just a reminder of how this works. And remember that ggplot, it needs to have that wider format, the longer format, right? So you change, remember, the wider to the longer format. If we just look at gene results here, if you remember the gene expression, this is what you would call wide format. Each variable has its own, for the most part, designation here. So one column for BRCA, one column T53. Tissue type is changed over to the wider format, but you do have the longer format, but the rest of everything is the other way. So how can we flip this in a way that can be used better for ggplot? So basically, we're pivoting longer, means we're pivoting in these three columns, and we're basically putting them into a new column that is referred to as gene, whereas values referred to expression. And let's see what this would actually look like here when we run this. Let's see, what are we missing? Don't need that pipe, right? And we need two, and there we go. When it's split up a little bit too much, it can lose that pipe and forget where it is. So now let's look at the difference. So now we've made a new column called genes, and that gene column has the three values in there, and then we have a column called expression, which is basically the expression of each one. So basically, we just taken those three columns, and put them into one column, and that's the way ggplot likes to call the different genes. So that's why we had to flip it back to there and pivot longer down to there. And then once we have that, we can just group by genes. We can stratify it out to our different genes. Makes it a lot easier to group by. And then we'll summarize based on that grouping, and we'll look at things like the mean, and we'll run an actual t-test within the summarize, and then we will kind of just do some interpretations. So just to kind of look at the t-test, exactly like before, but now that we have it flipped over to wide format, now we can do the expression by tissue type and not have to call those columns specifically. So if the columns are different, you have to call them differently, right? That's why we had to make the normal versus tumor, vectors here. But since now that we've switched it over to the pivot, it's a little bit easier to call just expression by tissue type here. And then here once again, and that gives us our statistic value, remember, and then we're looking at if we just want that, and then we're looking at the p-value for the same thing, expression by tissue type, and that gives us our p-value. So basically we're just saying, we want to call all of each of the genes, look at compare them across the different genes that they're against, and get their statistical p-value, right? And then we'll just say things like, we'll interpret it, is it normal or low, things like that, right? So doing this, summarizing it, it's just a two sample t-test among different things. And we see our mean expressions, our p-values. We see that our p-values are significant in the first two, which makes sense. There's a significant difference. And then we get the direction that it went down, and it actually went down significantly in BRCA1, which makes sense because it's the tumor pressure. It went up in MYC, which is an oncogene, which makes sense. And TP3 unfortunately didn't have significance change. It had a high p-value. So even though it goes up in tumor a little bit, it's not significant. There's not enough difference to make it. You can see here, it's very similar here. So BRCA1 goes down, MYC goes up, and these are about the same, which all makes, pretty good sense there. And just, how we drew this out, I just pivoted it longer once again to get it back in that new shape. And then I just did a GG plot of gene versus expression, obviously fill by the tissue type, because that's what we're looking at. And make a GM box plot, and we pretty much got you here. And one thing I wanted to show is one ways you could do, remember that sample compare means is the best way to add in significance values, but there's also a way to do it manually. Here's one way of doing it manually. I'm just basically annotating text. X equals 1, 2, 3 is just 1, 2, 3. Y is up and down. Higher value would be it would be up here if I put a higher value. And then what are we actually labeling here in this size? So I know these are significant to 3 stars. I know this is non-significant. So I was able to label all that out on my plot, directly and manually. So that's another way you could go. And you actually could just put your whole dash line there, You could put something like dash, your actual p-value, dash, and you would get the line there too. So there's ways you can do it manually like that. But one important thing to look at is we did multiple testing here. And in these instances, you can't just take the p-value for what it is. And this is why I wanted to kind of introduce this. If you're just doing 2 different populations, you don't have to worry about this. But if you're doing multiple, you really need to worry about multiple testing, because what happens is the more tests you do at once, the more likely it is that you're going to get a positive result that's not going to be real. And this really matters when you do things like 10,000 different comparisons, things like that. But even in 3, it matters. So basically, the threshold is changed. You need a stronger threshold in order to be, labeled basically as significant in these instances. And we will go back over that more later. So now that we've done kind of our unpaired tests so far, and things have been, are simple, are multiple, are just a simple sample t-test, or 2 sample t-tests. I can't talk today. And then that's what talk great. But what about if your values are paired? How do we do a paired t-test? How is that different? So basically, a paired t-test is comparing the same subjects basically at 2 different time points or under 2 conditions, but it's the same subject. It's not changing, right? Every value is not different. So for instance, we're taking the same patient, right? The same subject, and we're looking at 2 different time points, which happen to be 2 different conditions. And we're saying, did the PSA values for this patient change after treatment? So we're just looking at that PSA value in the same patient, same sampling, everything. And we're just looking at the comparison between, did this treatment, significantly to offer a change in PSA. And so if you remember, we have our paired biomarker data set, and I'm basically just going to select out some of the important columns: patient ID, PSA before and after, and the change. So just kind of simplify the data we need and kind of make a summary of that, basically. And I'm saying, basically, I'm grouping them I'm stratifying them into before, after, and change. And then I'm kind of just looking at the mean, standard deviation, everything, based on these different values. And we see here already, we're seeing the change is -14, and this refers to after minus before. So it has gone down, but how significantly, we don't know. Let's check it out. So one thing we can do to kind of get around this, or I guess we can kind of plot it out first to see what it looks like, right? Here I want to show you, I'm making kind of a cool plot here where you can actually see the paired differences here. And what I did here is I have my PSA paired, our subset column. I pivoted longer again. This time I have pivoted because I want the PSA before and after to be in one column called time. And then they have their PSA values, right? So that's how we've pivoted down there. And then I'm basically making them a factor. So I'm just basically saying factor of else time before, if not after. But the important thing is just making these things into factors. And actually setting the direction too, where I want before, first, after, next. And then I'm just doing a ggplot where x equals time and y equals PSA. And I'm making a GM line that it basically is set up where the group equals the patient ID. And then I set up a GM point for the color equals the time. So the color is going to equal the time before or after. This GM line between these two subjects creates this actually line connecting everything. So I think it's a pretty cool plot because you can just really cleanly see that things have gone down after the treatment for each patient. And it's important to see them per patient, right? It's the whole point of a paired analysis. And then we're just making another histogram like we did before, the density plot, just to show the differences. So just like before, we have our ggplot where x equals our PSA change. Our histogram is going to have our density as our y. And then we're going to overlay that GM density. And then we're going to set our lines at our mean normal values and our mean of what the change is, right? So we have our histogram. We have our density plot. We have what the no change value would be. And we see our data kind of falls pretty nicely in a negative value, negative 13 or whatever it said. So we see probably our data is significantly lower, but we don't know. We need to actually check now. So let's check for normality first. Remember, that's a quick way to do this. So Shapiro.test first, right? And so we can actually look at the changes in this instance. Since we have a column on PSA change, we want to see if the distribution of change is normal. That's what is important in our way, and we can also do it by the tidy way below here if we wanted to. So, but we're just doing Shapiro.test, PSA paired change. This time we're not doing the dollar sign thing, so we want everything to be along. We want to grab everything at once. We can call it later. And you can see here, that's what we do. We call the p-value column here. We can call the estimate if you wanted to. Here we just care about the p-value, and it is above 0.05. So this is a normal population in this instance, and it looks very normal, right? So that gives us the good feeling that it is normal going forward. And so let's do the actual t-test itself. T-test itself, what's the difference? Well, it's exactly the same. T.test, a vector of the PSA before versus the vector of PSA after. Just exactly like the above. The only difference is we do the paired equals true. And if we would have done it in tidyverse, it would have been the same thing. We would have done exactly the same way. We just added the paired.true. Nothing different. So that's able to get us our paired t-test, and we get a p-value pretty low here, well below 0.05. So we can have a pretty good feel that there is a significant difference there. And then we can plot them. And basically what we can do, alternatively here you can look, we could have done simpler before. We could have just checked a simple t-test since we had a simple population versus the normal of 0. That would have been an alternative way to do it, just letting you know, like our first version. And it wouldn't be a paired result in this instance. But we want to talk about what we're doing here in the newer way, so that's why we went with the paired equals true value. And calculating the coincide D is super easy, exactly like before. We just changed paired equals true instead of false. And then here below is your tidy way of doing it. So now we have everything, our p-value, our Cohen's effect, everything. So now we want to check back and just do our ggplot showing how everything looks. Really simple. The PSA, the paired column, remember I pivoted to longer to change up everything below, and we set the before and after as factors. It's really very similar to what you saw earlier when I set up everything for the plot here. It's just we're going a different way with the plot than before. So instead of doing the point way, we use ggplot x equals time, y equals PSA, and then filter by the tissue type, right? Or before or after, not tissue type, but time, right? Before or after. So we have time by PSA, and then fill by time to get the before or after. We had the box plot with no outliers. We had the jitter. We had that little diamond. And that gives us our plot overall, our differences. And then to add the p-values, once again, we use the stat compare means. We use t-test, var equals true, because it was. And then everything's exactly the same. There's no differences, except I'm taking, instead of paired equals false, I'm doing paired equals true. So paired's really easy. It's exactly the same thing in every way. You just add the paired equals true. So that makes things kind of easier there. And I just kind of added some summary statistics, and just to show that we saw that the treatment, effectively does reduce PA values at a decent large effect size at a highly significant p-value. So that's good. Easy way to do that. So what happens if we're trying to do these t-tests and these parametric tests aren't showing up? They aren't passing. So the distributions are not normal. They don't have equal variance, for example. So like these tests wouldn't work on these assumptions. So we need to have a non-parametric alternative to these tests. And lo and behold, we do. And it's basically called the Wilcox test. So if you're doing the two sample t-test, the most common, and your assumptions are failing, then you're going to want to use the Wilcox test. In this instance, for two sample, it's the Wilcoxon rank sum test. So let's look at some data that's non-parametric and see how we can apply this. So the assumption is, if it's not normal, then we use this, because it's not non-parametric, right? So I set up some skewed data here. It's just basically saying we have two groups, one's control, one's treatment, and after treatment, the mean value goes up. Don't worry about what that actually the mean value is, because this is just some pseudo toy example. We just want to show that the treatment group has higher values, basically, right? So once again, we looked at the data, we group by group to stratify, and made some summaries. It's so powerful, right? Just a group by whatever you want, and then stratify all your different things, right? So within the stratification, we will check for Shapiro.test for that biomarker column. We just want the p-value, and we want to see if it's above or below 0.05. And we see here, we have a very low p-value, so it's not over 0.05, so this is not normal. This distribution is not normal. And if you look a little bit into, so we'll look at that in a second. So the distributions are not normal, so we already know that. So we already have to be aware of that. And we could check them with histogram if we would like, or density plot. We would just see that they're going to be skewed here. And let's check equal variance. That's great. If they're not normal, that's okay. We have tests for that. What if they're equal variance? So we run the Levine test really quick, biomarker by group, by control versus treatment, and we get equal variance equals no. Oh no, this is not good. This is the worst thing that could have happened. So both our things failed. So, what do we do here? How do we go on? Well, let's just look at the data a little bit to see what's going on here. I basically made a histogram of each of the data and to see what it looked like, and you see that it's totally different, right? This really isn't normal. It's just like straight up the two columns and then tails off. This guy a little bit more normal, but I guess because of this big plot on the left and this just very skewed data here, very skewed. We definitely have a right skew here, or we have a long R tail moving the mean over too far to the right. So this is just it's a very skewed, non-normal population, and we see the treatment group is much, much worse, right? Or I actually wouldn't show it there, right? We'll have to look at the p-values separately, but treatment is much more skewed. So normally, if the equivariance was true, we would just jump it into a Wilcox test, no problem. That would be easy. If we just did the t-test result like before, we would once again just do like before, we would do biomarker by group. That would give us our t-test result. And if it was just normal, if the population was just abnormal, but everything else, the equivariance was actually, so if we had a normal population where the equivariance was false, I mean, the equivariance is true. So normal, false, equivariance is true. Very simple. You just use the Wilcox dot test. And it's exactly the same as t-test. You just do Wilcox dot test. Same with the tidy as well. You get your answer. Real simple. The problem here is you have the equivariance. Well, one way to get around this is to add exact equals false at the end. And if you add this, exact equals false, it mostly makes up for this variance difference. It basically samples from the distributions multiple times to get a better feel for what is going on in that distribution, and it's a little bit more robust, and it'll give you a pretty solid result, even with the equivariance equals false. But if you really get to the root of the problem and really feel like you're getting the really right data, you can use this Brunner-Munsell dot test, right? So you just call on the library Brunner-Munsell, you run Brunner-Munsell dot test, same way, just instead of t dot test, instead of Wilcox dot test, do Brunner-Munsell dot test. Biomarker by group, the data, and here you can do permutation true equals false. The more permutations, the more it's sampling from the data, the more chances it's having to shroud the data and kind of have a bigger population to make its decisions from. So, you know, unless you have a super slow computer, you want to do permutation true equals here, and this gives us our best result here. And if we throw all these into a data frame here, we can see that while they're all significant, there's much a more robust answer in the Brunner-Munsell. So since the Brunner-Munsell and the Wilcoxian both came out they were significant with a good p-value, I think we can get a pretty good feel that this is true. It's just true, and this is the way we would want to go, because this would be inappropriate to use the t-dot test in this instance. Just to kind of show you the comparisons, what you can do. In real life, you're pretty much going to have, you're just going to see a non-normal distribution with equal variance. So then you can just use Wilcoxon. I'd say if they both fail, try out the Brunner-Munsell. That's the way that kind of goes. So what if we have a paired data now? Paired t-test, right? Paired values. So let's kind of go back to our, let's see, we're going to basically make a new table with outliers, basically. So we're basically going to have another before and after treatment kind of thing. And we are going to say that, you know, the after, there's a negative effect, basically a negative pull down from that which is what we're looking for. So whatever we're doing, the treatment or whatever is going to drop down the after value to be negative. So what we're seeing here is if we've kind of visualized this, you know, we basically have patient IDs before and after numbers, and then we made our change equals after minus before. So after minus before, if we get a negative value, then that means things have gone down, right? Just to simplify that, we'll just put it in a plot here, paired with outliers. Basically, our y is equal to our change. X, we're just putting it equal to 1, because it's just one value, and or just one plot right here. And we add our GM box plot, our GM jitter. We're actually a horizontal line for 0. That would be no change. And what we're seeing here is there's a pretty significant change that goes down, but we see some huge outliers that go way down here. So we're kind of worried about that, like should they be used or not? So let's check the distributions here, like you would expect. So we do a normality test, right? And we're just doing our Shapiro.test here, and we'll just call our victim column just the change column alone. And we grabs our outliers, and this is with outliers basically, and we get a non-significant test. So that means we are normal. We are normal. Even with the outliers, we're normal, which is kind of unexpected. So that's good. So you could say, well, we could use our non-parametric test here. And we could. We could do our t-dot test, color before, color after, kind of like our PSA stuff, say paired equals true, and we could get our answer there. And we could feel pretty good about it, because it is normal. And you don't have the equal variance test, right, because you're doing pair data. And, here's you could do it with the tidyverse well here, just so you know. However, what the literature states that while a non-normal distribution of paired t-tests should use the t-dot test, if you have very big outliers like this that could jump out way far like that, it's in this instance, it's better to use the Wilcox test with outliers. So even though it is a parametric distribution, the outliers are so out that it still is better and more robust to use a Wilcox dot test. So this will be exactly the same, just Wilcox dot test instead of the heat dot test. And we get our result, and we see that it has, a little bit higher p-value, which may be more accurate. And we have so that they're both accurate, and they both could be used in this instance. But with outliers that far that you don't want to remove, probably best to use Wilcox. So that's why I kind of gave you some kind of a little complicated examples, because it'd be really easy to be like, oh, I have a 2-sample t-test. I want to use Wilcoxian rank sum. Everything's normal and equal variance. Let's just run a t-dot test. Let's just run a Wilcox dot test then, because everything's good. Sorry, I've been saying the opposite. Let's say we have a non-normal distribution, right? Well, we would jump in and use Wilcox. It's obvious, right? That's why I threw that first the equal variance, wrench in all this, which makes it a little bit more complicated, right? And lets you know you need to change Wilcox text or use the Brunner-Menzel. So it's just kind of throw a wrench in there. If it was not normal and everything else was fine, then just use the Wilcox test, no problem. If it's a little bit more complicated, then you know what to do to check out a little bit closer, right? And then just throw another wrench in your second one with the paired. Remember the paired, if it would have been, if it would have been non-normal, it would have been obvious too. Just jump right into Wilcox with paired. No, it would have been Wilcox paired, no problem. We don't have to worry about it, right? But since the outliers threw in a wrench, you had to think about it and maybe choose Wilcox. So I think when things play out the way you think, like the equal variance is true, the non-normality equals false, it's really easy to choose Wilcox test. But just showing you that there's some more complex ways of looking at it, because things don't always work out the way you think. Definitely, right? So next I want to talk really quickly about power analysis and sample size. And basically, power is the ability of finding a significant result when there really is a difference. So if you have low power, it's very possible that you're grabbing, you're missing real effects, right? So you want to get at least a power of 80%. I kind of just showed you a way that you can kind of make a use the R power.t.test, where basically we've listed a group of sample sizes and effect sizes that might be useful. We've talked about how the Cohen effect size calculator or function can be interpreted within this distribution, and we basically have, based on these effect size and sample size, assumptions, we've used power.t.test to plot out where, if we're doing a 2-sample test, where can we see significance of 0.05 with an 80% power at certain sample sizes. So what's our sample size need to be able to get this effect size at this power? So that's basically what we're plotting out here, where our x-axis is equals sample size, or y is the power, and the color is by our effect, right? So what we're looking at here, long story short, is if you have a very large effect, it's a lot easier to find, right? So you don't need as many samples. If you have kind of a medium effect, a little bit harder to find, so you need more samples, right? Number of samples is going here. A very small effect, you're going to need a lot of samples. So this is just a way to kind of give your reviewers confidence that you have enough sample size in your group to be able to grab the power for the effect you're looking for. And you kind of just have to go kind of in a circle of making calculations and resetting these things to be able to set them right for your experiment. So, once again, everything's just kind of summarized here, where you can see how the number of patients is going up the more subtle the effect size is. So that kind of makes sense. So just a little food for thought if you want to try to calculate those out. And there's some changes of these and alterations that you can do with these that we could do just for single cell. Like, how many single cells do I need to know to be able to grab this effect at this depth? There's ways of doing it that way too that we can go over later. They're really useful. All right, so we've kind of covered everything, but I want to go over just a few practice exercises to kind of just rehash it, have a little repetition, so it'll help you remember like what we're actually doing, okay? So here, the first thing we're going to do is, instead of BRCA1, we're going to test if MYC expression differs between tumor and normal tissue. So if you remember before, we just grab out what we need out of that expression data set. We just need sample ID, tissue type, normal or tumor, and our MYC, our gene we'll look at. We do our group by, right? We use our MYC data, we group by tissue type to get these split off, and then we do our summaries to get our data based on that, right? And then we're just going to do a quick look at this box plot. So X is tissue type, filled by tissue type, right? X is tissue type, filled by tissue type. Y is our MYC expression. We have our box plot and our jitter, and it kind of gives us our values where it looks like tumor expression is higher. So let's go ahead and test that. First we'll do the Shapiro, and we're basically grouped by tissue type, and we're just doing the Shapiro.statistic on MYC, and we're asking for the p-value. This is exactly like before, and we are getting that it is normal. So don't have to worry about that. We do our Levine test, MYC for tissue type, and we see that our equal variance is good. So we're in good shape here. We can just do the normal kind of t-test. So t.test, MYC by tissue type, super simple. var.equal equals true, because we know that's good. And that gives us kind of our answer there, our t-test. And then for our colon D, remember we just filter out our columns. So we want our rows, we just want all the rows that have the expression values of MYC that are tumor versus the ones that have normal. So basically just made a new data frame basically in a way, and use colon.d to get that effect. And then we're just gonna plot this results, and this is really easy. We just do the same plot as before. We're just adding the stat compare means, which is going to be a t-test, var equals equal. Everything's just really simple. So we're able to get that clean p-value between the two, showing the tumor went up. Okay, and we're just kind of rehashing that data here. We're saying the tumor went up and MYC is significantly higher in tumors, which makes sense, right? So let's do a simpler one. Let's compare Ki67 expression instead of tumor and normal. Let's do between p53 wild type and mutant. So we'll just switch it up a little bit, right? So we're going to make a data set here based on Ki67 expression, and it's going to have patient numbers. Basically, the patients will have a p53 status of wild type or mutant, and we will set up a number of patients that that have different expression values between those two things. And then we'll just simply grab our data, group by p53 status, remember group by, and we have mutant and wild type, and summarize our stuff. And we can clearly see that the mean is much higher in the mutant Ki67 expression, which makes sense because there's more proliferation there. And we'll just plot this really quick. P53 status filled by P53 status, Ki67 expression here. We add our GM violin, GM box plot, GM jitter, and that gives us our kind of clean different distributions here. It really feels like mutant is higher, but we need to go a little farther into the data. Looking at the distribution, I would say the wild type looks really good, but this mutant might not be super normal. So let's look more into that. So first we'll do our Shapiro test. We just grab our data, we group by P53 status, and we just summarize. And for one of our summaries, we do our p-test based on that. And by looking at that, we see that the mutant is actually not normal. So that's not good, right? So we can look at this two ways. We have wild type is normal, the mutant is not normal. So you have to think about this might not be the best thing for a parametric test. But look into it farther and look at the variances, right? If we do the Levine test for our variances, we see actually equal variance equals yes. So this is kind of confusing. One can go either way. Our variance is good. We're just simple t-tests. We're not paired. Our normal is half good, half not. So let's just kind of do it both ways to see what we get. So the question would be whether to use t-tot test or Wilcox dot test. For both of them, the var equals true and the paired equals false. So we just do the same thing, KI67 by 53 status, and we get our two values here. And then we also are going to do an effect size based on P23 status as well too. So the effect size won't affect which one of those things we use. And let's go on and plot that, same plot, and let's do our stat compare means. I'm going to do this by Wilcox test. Everything else is exactly the same, and that gives us our p-value here. So in an instance like this, it can go either way, but I would say since one of those populations is non-normal, it'd be better to go the Wilcox way in this instance, which makes a lot of sense. Good news is that they both are the same no matter way. We have a high Cohen's value either way, right? And we can say that P53 mutations, mutant tumors have a higher proliferation, which makes total sense, right? And just one more quick thing, just to remind you of visualizing these different things. If you have a big data set of variables, you can look at them beforehand here, right? And we're going to create a vector called continuous variables, which will be baseline tumor size, final tumor size, tumor reduction, and percent reduction. And we're basically taking our drug efficacy data set, and we're basically just selecting all of those continuous variables. We're pivoting them longer to basically make a variable column with all four of those things. So it'll be baseline tumor, final tumor, blah, blah, for each sample, and they'll have their value will be their expression value, right? And we're basically just going to group by variable, which will be our four different things, and we'll do our summary statistics. That gives us an idea of what's going on in those, and then we'll throw in our Shapiro test there as well at the end. And what we do when we find that is our percent reduction is, interestingly, not normal. So our baseline tumor size, our final tumor size, our tumor reduction in general are all pretty normal, right? So it's kind of weird. So we're not seeing a difference there in the percent reduction. So we need to kind of look at that and see what is going on here. So we just got to go ahead and I'm basically just selecting all the variables. So I'm selecting all. Remember, select is columns. I'm selecting all the columns, basically, that we talked about. I'm pivoting them longer, just the way we had before. Remember, I want the variables to be the four different guys. And I'm making a histogram, basically, and facet wrap to put them all on here. And we're kind of just looking at the histograms of the normality, right? So these three guys look really good normal. It makes sense why their values worked out like that. We can see the finals. The final one had the most normal. So this final one's the most normal. These are the two are the least normal. And then we had this guy who's just heavily left skewed with this long left tail pulling the mean out. So our percent reduction, interestingly, is highly skewed to the right, which may make sense because the treatments are all getting better, but it's kind of interesting. And going forward with this data, you'll be able to apply different parameters based on which things you were trying to actually compare. So one last thing, I want to go to one advanced topic that we will be using from now on, and it's extremely important, but people really don't think about it until they need it, is multiple testing corrections. So why do we really need these? So like, let's imagine we're testing 20 different genes, like a 20 gene panel, and we want to see the difference between the cancer and the normal tissues, right? If none of them were different, we'd still expect one to appear significant, because just by chance, let's say the p-value is 0.05, one of those 20 alone could already be positive just because we've done 20 tests, right? Or it'll be more than 20 tests. But since we tested them all, 1 out of 20 is going to end up, and it's not even true. It's not even significant. This is the multi-testing problem, right? If you compared that to just one other, it wouldn't be significant. So when we add on more things, we need to do multiple testing correction to change the threshold to be higher for this instance. So let's create a data set here. We're just creating a data set that's 20 genes and 30 samples per gene. Basically, 30 samples. For each sample, it has a gene, right? It just has 20 genes. And then out of these 20 genes, 18 do not differ by chance. Only 2 are real. We know that a priori beforehand. And a little bit fancy, I'm just throwing them all together into a matrix here. Don't worry too much about that. And let's look at what they look at. And basically, I see all my genes. They're going to have their control groups. This is the first, I looked at just the first 10. They're going to be control. If I looked at the other ones, you would see later on we would have the real ones here, which are 19 and 20, for example. And then we have our expression and we have our status. And like I said, if I called 19 and 20, they would have a real difference here. They would have their real difference. And then, the leads, the group below would actually have, your treatments too. So that's the way we can kind of look at this, all at once. And so anyway, we have our matrix now with the way we want to look at it, and let's just do t-tests now between every one of those, like we talked about, like Surad does, how we did earlier with the 3 genes, right? So we take our gene data, which is just those 20 genes. I group by gene because I want each one of my genes to be in columns, and then I summarize, and I'm basically looking, just for different summary statistics, but basically this p-test is what I care about. So I'm doing a t.test. So I guess we're just on these, we're just going to assume normality and equal variance just to get us kind of a little bit faster. But you really should check those first. But we have our gene data, group by gene, and we're doing our column of p-value, which is just t.test. Very simply, the expression of everybody that has treatment versus everybody that has control. It's just grabbing out the rows, and we're also doing a fold change. And when we do that, we find that 9 out of the 20 genes actually have significance without correction, right? So we feel really good about that, but we know that only 2 are truly different. So what can we do? How can we make some corrections here? So let's make some gene results. Let's change the gene results and add on corrections here. So we're going to add these different columns. And first, we're going to use the Bonifari method. So basically, we just do p.adjust what the p-value was, right? We have the p-value is up here. So p.adjust value and equals the method, right? So we're using Bonifari, the whole method, and the Jamini-Hochberg, which is FDR. And we're basically looking at these and comparing what our results are. And basically, we're using 0.05 as our significance for each of those values. And remember, if you look back to the old days, you could have done this simply if you grabbed one of them and to add onto your actual t-test using tidyverse. So another way to do it. I kind of like to see it all differently and add on later so I don't get confused. So now we have our results with our new multiple testing corrections. Let's just kind of grab out some of those columns and look at the head here. And what we see here, I grab the ones that have no real difference here. And what you'll see is, if you look at just the p-values without corrections, you will see that a lot of them are true, right? All of these guys have p-values less than 0.5, right? 0.034, 0.096. 0.02, these are all true. But if we do the corrections for using the Bonferroni, they're all false. And actually pretty horrible, a lot of them. And if we use the FDR, we see that now we have 1, 2, 3, for 5 false positives instead of 7 false positives. So really, FDR is the easiest, lightest way to look for this. And you can be able to do a lot of discovery, but you're likely to find false positives. If you use Bonferroni, it's a very tight, very stringent. This is the one I use normally, and you're going to have a lot more faith in those results being real. So if you look at here, no correction had 2 false positives and 7 false positives. So it's doing good at finding the ones that are real, but it's not good at finding the false positives, right? So that's why I had kind of a higher FDR. For the Bonferroni and the Home, they basically did a perfect job. They found everything that you would expect, and we didn't really get to stratify it here, but Home is a kind of a middle ground approach between Bonferroni and FDR. For the FDR, it found 5 false positives still, so it threw off its false discovery rate, but maybe one of those would be interesting to look at too. So it's hard to say. So it's Home's kind of the middle ground approach. Bonferroni is the most significant. If I kind of make a plot of those, you kind of can see what happened here with the p-values. For the no correction, the green ones are the ones that are actually significant. The red line is you need to be above that to be significant, and then the other gray ones that go above the red line are the false discoveries, right? So 1, 2, 3, 4, 5, 6, 7 here had false discoveries. 1, 2, 3, 4, 5 for the FDR. But for Home and Bonferroni, you can see that these genes have been pushed down really low, and the signal's really strong here on the correct ones. So in this instance, we would be able to trust, Bonferroni to give us our actual real values, which makes just a big deal between 2 and 9 significant genes when you're doing a genomic panel, right? And here's just kind of some of the corrections for, and you can think about, if you're testing a few specific hypotheses, you can use something like Bonferroni. If you're doing a really big exploratory analysis, maybe FDR. If you don't want any false positives at all, use Baroni. If you want some, use FDR. And you kind of think about this as, I think it's really good with the fishing here, where if there's no correction, you're just using a huge net and you're catching everything, including the trash, right? The fish and the trash. The Baroni is using a tiny hook, so you're only getting the best fish, right? FDR is using kind of a smaller net, so you catch a lot of fish, but also some trash too. Trash equals false positive. So that's kind of a way of looking at it. How wide of net do you want to cast out there? So let's go back to we looked at our 3 genes, our BRCA1, TP53, and MYC at the very beginning, and we did our plots, but we didn't know if they were actually real or not, right? They seem significant, non-significant. So here I basically just redid our thing, and I just added the Bonifarian FDR p-dot adjust methods here, and just added it back to our table. And our original thing that we did at the top, TP53 is the one that failed, and so it didn't have a significant value. Bonferroni is basically saying the same thing, and even FDR is saying the same thing. So there's no significance on this gene, even after multiple correcting. So now we can put that up there as our p-value. Our adjusted p-value, people will believe us more. And more likely to be, even though we know the value, it'll be a much more robust test, and people will have more reason to believe it. And you can see here that the threshold with 3 samples already went down to 0.01. So we're increasing that threshold, depending on what's going on with how many samples you have to meet that multiple testing criteria. All right, so key takeaways. What did we learn today? We learned, how I was complaining about hypotheses and how they should be now, and p-values aren't low enough. So that was my complaining, so that was our null hypothesis framework. Just me on a stump talking, and then what we really the crux of the lesson was the 3 types of t-test, right? The 1 sample t-test comparing one group to known value. The 2 sample compares independent groups, right? And the paired sample compares the same subjects twice. And we talked about our normality assumptions, where we test for Shapiro-Wilk for normality. We use Levene's for equal variance. And if these things fail, we use the non-parametric test, but it's kind of complicated when we talked about with your equal variance and our outliers. So it's not completely obvious, but I think you get the overall idea. And our non-parametric alternatives are our Wilt Wilcox rank sum tests for 2 sample, or Wilcox sign rank tests for just alternative, to a pair t-test. And really think about that when the data is skewed or has outliers. Also, the effect size does matter. It tells you how much of a difference is, and this is really important, and just knowing how much the difference is, and also in calculating power sizes to know what our sample sizes we need to actually get the answers we want in a reasonable way. And we did multiple testing using, looking at the family-wise error rate and making various corrections based on, 3 popular methods of Bonferri, Holm, and FDR. So that's great. I think I'm really glad you guys attended today, and I think it's a very practical lesson. You can learn a lot of things that if you've forgotten, or at least learn how to calculate the p-values, right? So next week we'll learn more about comparing more than 2 groups using things like ANOVA, and see which groups differ more, like doing things like post hoc tests. We'll do more multiple testing, more correction for that, and we'll look at factorial designs, testing multiple factors at once, just kind of taking these t-tests up to the higher level, and we'll kind of put this behind us, and then later on we'll move to cooler things like linear regression, survival analysis, things like that. And I've also added an additional assignment, kind of a homework that I've given you guys, and I have basically all the questions and all the answers. You have every single answer for everything. So if you have a chance, it'd be great if you could kind of go through these. Maybe first kind of go back through the examples in the data today, make sure you understand them, you can recreate them. If you want to go a little more in depth, try out this additional assignment. You can just do even parts of it if you want, but we're really just doing basic t-tests that we've done, and doing some multiple correction for them, and then as a bonus, playing around with the power analysis. Nothing we haven't done all the lesson today, and I think it would be great if you could spend some time going through that. If you have time, I know you're busy. If not, I have all the answers to at least go through those as well. Some additional resources, we talked about that R for statistics, Hadley-Wickham book is always the best. That's the one you should be really looking in to go forward. If you want to know some things about specific things we talked about today, you can look at these resources for the effect size calculator, power analysis, and multiple testing corrections. But I guess this week, this concludes our session, our second week of the R statistics workshop. I thought we did a good job of covering some very basic overall things that we use all the time. And feel free to check out, the additional assignment, additional resources as needed. And I will see you guys in week 3 for the next lesson. And I appreciate everyone for showing up and are listening at home. And I guess that's it. Thanks, guys.